Everybody. So we're going to do a few trig limits here. These are some limits that turn out to be pretty useful for us in some of the coming things that we need to do. And so we want to work them out so we can kind of have them in our toolbox to use over and over again. I'm not going to strictly prove them. We're going to use some geometric intuition in a lot of spots, a little bit of algebra here and there to get the idea, but these won't be super formal proofs. We'll start with a couple of simple ones and then move on to some more, a couple more difficult ones. So let's start with this one. I want to look at the limit as theta goes to 0 of the sine of theta, right? This could be x goes to 0 of sine of x. Theta is traditionally what we use when we're talking about trig functions. We often use it. So let's just mix things up a little bit. So I've started a little drawing here to help us out. So I've got an angle placed at the origin with its one arm on the positive x-axis, and then the angle is rotating in the counterclockwise way around somewhere up in the first quadrant, okay? And so this is the traditional place that we put it, this is the conventional place that we put things. This is our unit circle, so remember its radius is 1, which means this section of the angle between the origin and the circle is length 1. I want to label a couple of spots. Well, let's do something else first. So one thing I want us to remember is by the definition of radian measures, we're going to do everything in radians when we're doing calculus. With the rare exception that something's applied, we might do some conversions when there's an angle measure given. But radians work a little bit easier with calculus, so we're going to stick with that. So the definition, by the definition of radian measure, the length of this arc right here is also theta, right? So this little curved piece from where the angle intersects up here to where the angle intersects down there has a length of theta, okay? So the theta in the center, that's the angle measure, is the same number as the length of that arc. The difference is one's a length and one's a simple number. The measure, or the definition tells us that the radian measure is the ratio of this arc length to the radius. Since the radius is 1, it's just theta. The difference is the angle has no units, and this has whatever length we're in. Okay, so those two pieces we have in. I want to drop. That's terrible. Let's see if we make that a little nicer. Maybe I'll go a little thinner for this. So I want to drop a perpendicular line down here. All right, so we've got a little right angle there. And let's call that, it doesn't matter, but I just want to stick with my notes so I don't confuse myself. I'll call that point A, this point B. And then one more line I'm going to draw in for now. We'll probably draw a couple more later. So this I'll call point C. So the first thing I want to note is that this is by the definition of sine. That length AB is the sine of theta. Okay, I'm being a little bit loose here with things that are lengths versus not, but just numbers, but it's not going to really matter too much. So, right, this is our definition of sine, right? Technically, the definition would be the y coordinate of this point. But I want to do it this way because it's going to help us kind of see the picture, and I don't have to keep stopping and saying the y coordinate, which is equivalent to the length, blah, 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 blah. So that length there, I can write it in here as well, is sine of theta. That's the length of this. okay? So from this picture, notice that the length AB is less than the length BC, right? Because we've got a right triangle there. BC is the hypotenuse of that triangle. It's going to be longer, which is less than the length of the arc BC, meaning that curved red section, right? If you walk in a straight line, it's shorter than if you walk in that curved path around it. Okay, we're gonna take that on intuition. Okay, and what else do we want to say? Oh, so what I can write with this, I'm going to look at the end here, AB and the arc BC. AB we already know is the same value as the sine of theta, and the arc BC we know is the same as theta. Okay. And we are dealing strictly with positive angles right now. I'm looking from starting at 0, where we'd be in the horizontal direction, and moving in that counterclockwise direction. So all of this is going to be positive. Okay. Well, notice what we have. We have the function we're interested in, this limit of sine theta as theta goes to 0, pinned between these two functions. Both of these functions, the limit as theta goes to 0, well, the function on the left is just 0. Its limit is just 0, and the limit as theta goes to 0 of theta is also 0. Right? These are from our limit laws. And so we get the squeeze theorem. Since the two outer functions go to 0, the thing in between them must also be 0. And so this limit is 0 by the squeeze theorem. Oops. Okay. All right, so and it should make some intuitive sense, right? If you start closing that angle, that height there from B down to the horizontal axis, if you close it, gets smaller and smaller, right? Now, of course, we should look from both directions because we were really looking from the positive side, right? I'm going to write this because we can make the same geometric argument, flipping it upside down, and just using some negatives in there. I'll let you work that out, but it's really the same idea that from the other side, the same thing happens, just coming from the other direction. And so we're going to take this now as a limit that we know. Okay. Another limit we want, let's see, I want the limit as theta goes to 0, the cosine of theta. Well, we're going to use a little bit of a trig and some algebra here. Cosine of theta is just 1 minus sine squared theta, square root of that. Well, we can apply a whole bunch of our limit laws, right? I can bring this limit inside, and I can also apply it to each piece of the subtraction problem individually. The limit of that constant is just 1. This, we can apply that law that lets me take the limit inside the variable, and we just found out that the limit of sine as theta goes to 0, sine theta is 0. So when we square that, we get 0. We get the square root of 1 is just 1. So we get that the limit as theta goes to 0, cosine of theta is equal to 1. Again, we need to use a little more rigor if this is going to be a full proof, but this is the basic idea. Okay. So here is our here are our first two simple limits that we're going to use to now prove some more complicated ones. So here's a big one for us. This is one that shows up in all kinds of places. This is the limit as theta Actually, let's start on a new page. I want to get this a little more organized. So I'm going to use the same drawing. So let's copy this guy. And let's get ourselves a new page. All right, just need this piece of it. Okay, and I'm just going to write down what we have. We've got the limit as theta goes to 0 of sine theta is equal to 0, and the limit as theta goes to 0 of cosine of theta is equal to 1. And the limit we want to show now is the limit as theta goes to 0 of sine theta over theta. So let me start with the end. This limit turns out to be 1. Let's say a few words about this. What it's telling me is that when we have small theta, really small angles, the sine of an angle and the angle is approximately the same thing, right? So if you squeeze this angle shut, right? As you get closer and closer, as the point B gets really close to the point C, that vertical length gets incredibly small at the same time that the angle does. And they get incredibly small at kind of the same rate, right? When we have these two limits being equal to 1, another way to say this is that sine of theta is approximately theta near 0, right? That's another way to conceptualize what this limit is telling us, that as we approach 0, it's like dividing something by itself. It's not exactly like it, but it's getting really close to it. Here's one of those things, near depends on what you're doing. Physicists use this approximation in a few different places. I'm sure other scientists do too. If you're a small enough theta and you can live with the small amount of error that happens, it's sometimes a convenient approximation to make. If you can recall the graph of sine, which looks like this. Well, the graph of the variable theta, if you just have y equals theta, is just a line through the origin, right? Well, when you zoom in here, when you look closely at this region near 0, these two graphs are very similar, right? Farther away, they're wildly different, right? Theta, the line theta just keeps growing as we go to the right, whereas sine just keeps oscillating between -1 and 1. So they become wildly different. But near 0, their graphs look very similar. And that's one way to interpret what this limit means. Okay, now let's go ahead and figure out how to show that this is the case. Let me move my drawing now. We're going to need to do a few more things with it. I need a little space. Okay. So we've already got from the work we did previously, we know that sine of theta is less than theta, right? And you can see that was what we did up above, where we looked at this vertical length between A and B and compared it to this curved length between A and C, right? And we compared them to, first we compared that line AB to the line BC, and then compared that to theta, right? And it's getting bigger as we moved along. And so that we had that theta was bigger. We can divide both sides by theta. Again, we're just looking at the positive side right now, and rewrite this as sine theta over theta is less than 1. Okay, so we're just going to hold on to this for now. All right, let's now add something to this drawing. I'm going to draw, or attempt to draw, a vertical line up here. I'm going to extend that line there. I'm going to call that point What did I call it? E. And I'm going to also draw in a line perpendicular to that blue line there. Okay, that's going to intersect this line at the point D. Okay, so I'm just drawing those lines in. So what do we know? We know that theta has the same measure as that arc BC, right? So we discussed that in the beginning by the definition of radians. Okay. Well, looking at that arc BC, I'm going to put that there just to mean the length. I can say that that is less than BD plus DC. Okay, so if you look at this line here and then going down, I think it's pretty clear that that is a larger distance. Okay, and these are less than ED plus DC. Why do we know this? Well, what have I done? I've replaced BD with ED. So BD is here, ED is here. They're part of a right triangle. ED is the hypotenuse. It's going to be longer than BD. So I've got the same summation, except I've replaced one line with something smaller. So I've got something bigger. That whole thing is simply EC, this big, tall line here. So what this leads us to, let's put this over here, is that we now have theta less than EC, right? So theta is equal to this arc BC, which is less than this thing, BD plus DC, which is less than ED plus DC, which is equal to EC. So since theta was at the beginning and things only stayed the same or got bigger, theta is going to be smaller than those things. Okay. Now let's look at another thing. I'm going to redraw part of the drawing that we have so far, just to focus on the parts I care the most about. Oops. This should be flat. Okay, so there's my origin. Here's the point C. Here's the point E. So I'm taking that big blue triangle now and drawing this smaller one. I'm also going to put in this point here. Now, remember, we said this side is sine of theta. That's the definition of sine. If you go back to your trig, this distance between the origin and A is cosine of theta. So we can use similar triangles here. So if I look at the ratio of sine theta over cosine theta, right? This is this vertical side over this horizontal side, because these are similar triangles, right? They share this angle. These two sides are parallel, right? These are similar triangles here. These are both right angles, which means that these two angles have to be the same. We've got similar triangles, so the ratios have to be the same, which means EC over OC, the origin to C, has to be the same. However, what is OC? That's the difference from the origin out to this point C, which is on our unit circle, so that's just 1. Okay? In other words, sine theta over cosine theta is tangent, let's leave it as, that is tangent of theta, but I'm going to just leave it as sine theta cosine theta, because that's how I'm going to need it. Sine theta over cosine theta is equal to EC. Okay. All right, we're almost there. We know theta right? We already knew that theta was less than EC, but now we know that theta is less than sine theta over cosine theta, right? Because we're taking this and putting it in there, which is another way of saying, let's rearrange this thing. If I multiply both sides by cosine and divide by theta, I've got cosine of theta is less than sine theta over theta, right? So that's just rearranging this inequality. Remember, we have this one, sine theta over theta is less than 1. So now I've got sine theta over theta pinned between these two functions. We already know that the limit as theta goes to 0 of cosine of theta is equal to 1. And the limit as theta goes to 0 of the function 1 is 1. Changing theta doesn't change the number 1. So by the squeeze theorem, the limit as theta goes to 0 of sine theta over theta must be 1. Okay, and this is a pretty handy little limit to have in our pocket. So we can now cite this as we need to without having to justify it. This is as deeply as we need to justify it now. Okay. All right, one last one. This is a little bit more straightforward. Instead of doing all this geometric stuff, which you could probably do it, I don't think that I've ever done it that way, but this could probably be done with that. We're going to use some of what we have now, do one more limit. The limit as theta goes to 0 of 1 minus cosine of theta over theta. So I want to compute this limit. The first thing I'm going to do is multiply it by 1. But the way in which I'm going to write 1 is 1 plus cosine theta over 1 plus cosine theta. All right, so I'm just taking that thing and multiplying it by 1, and I'm getting the limit as theta goes to 0. So in the numerator, I'll get 1 minus cosine squared theta. And the denominator, I'm just going to leave that as theta times 1 plus cosine theta. All right, so then we get the numerator. That's a trig identity. That's sine squared theta. We've still got theta times 1 plus cosine of theta. Let's peel off one of those factors of sine. We've still got another factor. And then we're going to use some limit laws. I know that I can split this into two limits as long as both of these exist, and we're about to find out that they do. If it turned out one of them didn't, we just go back and try something else, but in this case they will. So limit of sine theta over theta as theta goes to 0, we just did, is 1. This one on the right, we use the limit law to split. Let's write it out. These are still new, so we'll write them out. We're going to take the limit of the top divided by the limit of the bottom, and on the bottom, I'm going to split it. Oops, I wrote 1. That should be 0. Cosine theta. All right, so now I've got this 1 out front. I don't need to write that. The limit of sine of theta, as the limit as theta goes to 0 of sine of theta, we just discovered was theta. In the denominator, I've got 1. We know that cosine theta goes to 1. So I've got 0 over 1 plus 1 or 2, or 0. So the limit as theta goes to 0 of 1 minus cosine theta over theta equals 0. So we've got 4 handy limits now. The limit as theta goes to 0 of sine of theta is equal to 0. The limit as theta goes to 0 of cosine theta is 1. The limit as theta goes to 0 of 1 minus cosine theta over theta is equal to 0, and the limit as theta goes to 0 of sine theta over theta is equal to 1. Okay, so we can use all of these now at our discretion without having to justify them. The very last thing I want to point out, if you notice the numerator and the denominator of these last two fractions, right? The numerator right here has a limit of 0 because cosine goes to 1, we get 1 minus 1. The numerator's limit is 0. The bottom obviously goes to 0 because it's the limit of theta goes to 0 of theta. We get 0 over 0 if we're to take the limits of the numerator and the denominator. The same thing happens here. We get 0 over 0, right? Sine theta goes to 0 and theta goes to 0. So it's just interesting to note that we know that we're not allowed to use the rule, right? If you remember the limit law, if we took the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f of x over the limit as x goes to a of g of x, we're only allowed to use this rule as long as the limit as x goes to a of g of x is not equal to 0. So in this case, it is. So we can't use that rule. But it shows you a little hint of what happens. We can't make any assumptions. 0 over 0 in this case ended up being something that was getting closer to 0, and in the second case ended up being something that was getting closer to 1. And those aren't the only two options. It could have been doing something else. And so having the 0 over 0, we sometimes call this the indeterminate form. We don't know what it does, and it's very common to make a mistake to think that it must go to 0 or it must go to 1. People think 0 over 0 must mean 1, or they just see a 0 and say it must be 0. That's what happened in these two cases, but a million other things could happen. And so we can't make any assumptions, and this is one of the reasons we went through these, because we're going to need these and we don't want to get confused by the 0 over 0. Okay, that's it for this. Thanks, everybody. I will see you next time.